Hello, everyone. In this presentation, we are going to talk about Slack's DNSSEC rollout and a very interesting outage that we had on September 30th last year. I'll start by introducing myself. My name is Rafael de Elvira, and I am a senior software engineer on the traffic team at Slack. Our team looks after ingress load balancing, TLS, DNS, CDNs, and DDoS protection at Slack, among other things. During this talk, I'm going to pretend to be a DNS expert, but that's something I am really not. So let's go. So what is DNSSEC? DNSSEC is a suite of extensions intended for securing data exchange by the DNS protocol. This protocol provides cryptographic authentication of data, authenticated denial of existence, and data integrity, but not availability or confidentiality. These are the record and key types used by DNSSEC, which I will be referencing later on along the talk. So the first one is the TS record, and this is the delegation signer. It's used to secure delegations between name servers, and we also reference to this record as the chain of trust. Then we have the DNS key record, which holds the public key that resolvers can use to verify the DNSSEC signatures in the RRSIG records. These RRSIG records hold the DNSSEC signature for a record set. Resolvers can verify the signature with a public key stored in the DNS key record that we just mentioned. And then we have NSEC and NSEC3 records. And these can be used by resolvers to verify the non-existence of a record name and type. Then in terms of keys, we have the zone signing key, which is the private portion of the key. And this key just digitally signs each record set in the zone, while the public portion, the DNS key, verifies the signature itself. Then the key signing key will sign the public key exclusively, which is the DNS key, creating an RRSIG record for it. Here's a successful DNS record request sequence where the user will make a request to the recursive resolver, and then the recursive resolver will attempt to track down the DNS record that the user will just requested. It does this by making a series of requests until it reaches the authoritative DNS name server for the requested record, which is slack.com in this case. And this is a very basic interpretation of a DNS record request. And then the sequence is the same when the resolver does DNSSEC validation. The only difference is that the additional records requested and returned to perform this validation. And let's keep in mind that DNSSEC only validates the DNS responses received up to the recursive resolver, and it just ensures that the request, it hasn't been tampered with in transit, and is legitimately what the authoritative name server has. But bad actors can still man in the middle between the recursive resolver and the end user. Now that we've briefly touched base on DNSSEC, let's go through our DNSSEC journey at Slack. Back in May last year, we started off by doing a proof of concept where we replicated most of our DNS use cases on a controlled and isolated environment. In this environment, we carried multiple tests and gained knowledge on how to operate DNSSEC. Once our proof of concept was successfully completed, we worked on an internal RFC that outlined all the necessary work to enable DNSSEC signing on all Slack domains. Then, prior to starting the work to enable DNSSEC signing on any of these domains, we spent significant time simplifying our DNS setup and making some necessary zone changes in preparation for DNSSEC. I'm not going to cover these changes today, but feel free to reach out to me after the talk if you're interested, because we did a fair bit of work here. Once we deemed our zones to be ready for DNSSEC, we started with the actual rollout plan. By design, DNSSEC can only be enabled on a per domain basis, making it impossible to enable DNSSEC on a per subdomain or subzone basis. So this design choice significantly increases the risk of DNSSEC rollouts. To overcome this, we categorized all our domains by the risk, basically. So we have low, medium, and high. In this way, in the case of failed attempt or any bugs in the early stages, we would only impact domains that are used for things like monitoring or other non-critical or less impactful Slack features. For each of these domains, we followed the same extensive testing and validation steps, making sure that all the domains were still resolving correctly after DNSSEC signing was enabled. And at this point, you must be thinking, yeah, but how did it all go wrong? So as you might have already guessed, Slack.com was the last domain on our DNSSEC rollout. And prior to Slack.com, we rolled out DNSSEC to all other Slack public domains successfully, with no internal or customer impact. But obviously, Slack.com had to be different. So in this section, we're going to cover the 3 times we failed to roll out DNSSEC to Slack.com. So first, on September 7th last year, we did our first attempt to enable DNSSEC signing on Slack.com. However, prior to publishing the Slack.com DS record at the DNS registrar, which is the last step of a DNSSEC rollout, a large ISP in the US had an outage, and many of our customers reported being unable to access Slack as a result. Early in that incident, and before we were even aware of this ISP issue, we decided to roll back the Slack.com zone changes as a precaution. One day later, on September 7th, we enabled DNSSEC signing on Slack.com following the same procedure as on the previous attempt. And again, prior to publishing the DS record, our customer experience team noticed a small number of users reporting DNS resolution problems. So we started investigating, and we realized most of the affected users were accessing Slack through a VPN provider. And once again, we decided to roll back signing in Slack.com zones as a precaution. Then after further investigation, it turned out that some resolvers become more strict when DNSSEC signing is enabled at the authoritative name servers, even before the DS records are published to the .com name servers in this case. So this strict DNSSEC enforcement will reject a CNAME record at the apex of a zone, included the apex of a subzone, which was our case. So this was the reason that customers using VPN providers were disproportionately affected, as many VPN providers use resolvers with this behavior. So to overcome this problem, all our subdelegated zones were updated to alias records rather than CNAMEs. Then, after migrating all the CNAMEs at the apex of subzones, we were ready for another attempt, right? So on September 30th, and after careful planning, we made our third attempt to enable DNSSEC signing on Slack.com. So we started off by first enabling signing on the authoritative name servers and the delegated subzones as the last 2 changes, and we left the soak time prior to publishing the DS record at the registrar, as we had seen issues on the previous 2 attempts. Then after 3-hour soak time and successful validations, we were pretty confident to publish the Slack.com DS record at the registrar. And this basically instructed resolvers to start validating DNS requests for Slack.com. So at this point, we had fully enabled DNSSEC signing for Slack.com. And everything looked great for a while. All our tests, our external probes, our monitoring were looking good. And we were so happy to have completed the last domain on our DNSSEC rollout. But then after a little while, things started to look a bit less idyllic. Our customer experience team again started getting reports from users seeing DNS resolution errors in their Slack clients. So to give you some context, Slack applications are based on Chromium, and they integrate a way to export a netlog capture. This netlog capture is an event logging mechanism for Chrome's network stack to help debug problems and analyze performance. Netlogs are extensively used at Slack. On the left, you will find the DNS configuration of a client available inside the netlog capture. And on the right, you will see an attempt to resolve app.slack.com with all the relevant information. So during our initial investigation, all the reports were caused by no data or empty DNS responses from some DNS recursive resolvers, most of which were from a large customer using a private corporate resolver and from Google public resolver. So that's quite 8. And we were both surprised and confused by this, as Google DNS failing to resolve Slack.com should mean a much larger impact than our monitoring and customer reports indicated. So given the data we had at the time, we decided to roll back our changes for Slack.com. Then we attempted to do so by pulling the DS record from the DNS registrar, effectively removing the Slack.com DS record at the .com zone to basically stop the bleeding, so we could later focus on the no data DNS responses reported by customers. But after nearly an hour, there were no signs of improvement and the error rates remained stable. So our traffic team was confident that reverting the DS record at the registrar was sufficient to eventually mitigate the DNS resolution problems. But as things were not getting any better, and given the severity of the incident, we decided to roll back one step further. This was a bad idea. So, we rolled back DNSSEC signing in our Slack.com authoritative and delegated zones, wanting to recover our DNS configuration to the last previous healthy state, allowing us to completely rule out DNSSEC as a problem during the incident. So we had this false sense of trust in rolling back the zone signing changes due to the previous 2 attempts where we had done this successfully, with the slight difference of publishing the DS record at the registrar this time. So as soon as the rollback was pushed out, things got much worse. So this is an example DNS resolution alert that paged our traffic team. So yeah, that was me that day. It basically said that Slack.com was failing to resolve from multiple resolvers and probes around the world. This is not a page you want to get, by the way. So our understanding at the time was, and what we expected was that the DS records at the .com zone were never cached. So pulling it from the registrar would cause resolvers to immediately stop performing DNS validation. Then this assumption turned out to be somewhat untrue, as the .com zone will ask resolvers to cache the Slack.com DS record for 24 hours by default. Yeah, so we knew stop signing the authoritative zone is a high-risk operation unless the DS record is not published anymore. However, the assumption of no cached DS records at the .com zone made us think we were in the same state as the previous 2 rollbacks, having the same end result. However, unlike our previous attempts, this time resolvers had cached the DS record for up to 24 hours once the rollback was completed. So at this point, all validating resolvers that had recently cached this DS record started returning serve fails for Slack.com lookups. We quickly realized the mistake we had just made, and we started contacting major ISPs and operators that run public DNS resolvers, asking them to flush all the cached records for Slack.com. Additionally, we proactively flushed caches for resolvers that offer a public site like Google Quad 8 or Cloudflare Quad 1. So as resolvers flushed their caches, we slowly saw signs of improvement on our internal monitoring. So Slack clients send their telemetry to a different domain called SlackB. And thanks to this isolation, we were still able to receive client metrics that helped us quantify the impact of this outage. Ironically, SlackB had DNSSEC enabled successfully prior to this incident. So throughout the incident, we considered resigning the Slack.com zone without publishing again the DS record at the .com zone, as restoring would slightly improve the situation for some users, but it wouldn't have solved the issue with all the users that were initially getting these no data responses after signing was enabled. So for us to restore signing, we would have had to recover the key signing key that had been deleted when we rolled back the changes to the Slack.com zone. So in RAW53, the key signing key is managed by AWS KMS key. So KMS is an AWS service to store keys securely, basically. So this KMS key was recoverable as per our configuration, meaning that the key signing key would be the same, but we were uncertain if the zone signing key would have been there the same or different, as the zone signing key is fully managed by AWS and we have no visibility into it. So now, after the incident, Amazon's RAW53 team confirmed that the zone signing key would indeed have been different, as when re-enabling signing on the zone signing key will be generated with a new key pair, meaning that all DNSSEC validating resolvers would have continued failing to validate, at least until the DNS key TTL expired. So during the incident, we decided not to restore signing due to a lack of confidence, but we now know it wouldn't have helped, kind of. So at this point, and some hours into the incident, we were in a situation where Slack was resolving correctly for the vast majority of customers, but a long tail of users of smaller DNS resolvers, which had not flushed the Slack.com DS records, were still impacted. Then, as public resolvers caches were flushed and the 24-hour TTL on Slack.com expired, the error rates went back to normal. So at this point, all we had left was a mystery to solve. So once the impact to Slack customers was mitigated, we aimed to determine the root cause of this outage. So prior to attempting DNSSEC on Slack.com, our team had successfully enabled DNSSEC on all other Slack public domains. So we had a lot of questions, right? So how was Slack.com different? Why did we not see any issues with any of the previous domains? And why did this only impact some customer or like corporate internal DNS resolvers and some of Google public DNS lookups, but not all of it? To understand what happened, we replicated the rollout steps using a test zone setup, which was set up identical to Slack.com, using a resolver that we knew had problems during the outage. Surprisingly, all our attempts to reproduce this behavior were unsuccessful. And at this point, we were like, let's go back to the net logs that we have received from the customers during the outage and see what can we get from them. And here's where we found an extremely interesting clue. Clients were able to resolve Slack.com successfully during the incident, but they failed to resolve app.slack.com. Why? This indicated that there was likely a problem with the start.slack.com wildcard record, to which we thought, oh, like none of the other zones where we've done DNSSEC in the past contain a wildcard record. This is the only one. So this was clearly an oversight that we did not test the domain with a wildcard record before attempting Slack.com. So we collected evidence and we reached out to the Amazon Route53 team, who jumped on a call with us to figure it out. And after walking them through the evidence we had, they quickly correlated this behavior to an issue with NSEC responses that Route53 generated on wildcard records. When a request is made to a DNSSEC enabled domain for a wildcard record which type does not exist, for example, a query record type, the answer is a signed NSEC record, confirming that while the domain name exists, the requested type does not. This signed NSEC response can include some additional information specifically designed to not break wildcard records, but Route53 was not returning this additional information. Then what this means is that when a client does a query lookup for app.slack.com, it would correctly return a signed NSEC saying there is no record for that. And this is correct since we don't publish any query records in this zone. So the expected client behavior then is to fall back to requesting an A record. But since Route53 isn't returning that extra information, some public resolvers take that response to mean no other record type exists for this record name. So there's no need to query for an A record again. This NSEC response comes with a TTL. So it will be cached by resolvers, meaning that impacted DNS resolvers were being unintentionally cache poisoned by clients innocently checking for the existence of query records. Luckily, this cache poisoning would only affect the regional cache, which means only users of an impacted regional cache for one of these resolvers would be affected, while other regional caches would not. So once we knew this, and we were able to reproduce this issue against our test zone using Google DNS, but not using Cloudflare DNS, for example. So we had a second mystery, which was whether or not one of these major public resolvers was out of spec. We went back to reading the DNS RFCs, and we found out it is protocol compliant to reuse a cached NSEC record to decide a subsequent response, and this is called aggressive NSEC. And it's an optional spec that Google DNS implements. So in the end, we concluded that both options were acceptable, and the only real way to avoid being in this ambiguous situation is for your authoritative name server to correctly return existing record types in the NSEC bitmap. So our mystery was finally solved, and after a bit of time, the Route53 team fixed this NSEC type bug described above, together with a fix to allow recovering the same zone signing key if you re-enable signing on a zone within a time frame. We are very sorry for the impact this outage had on everyone who uses Slack, and we hope that this talk will shed some light on some of the corner cases with DNSSEC, and maybe this will prevent someone else from having a similar issue in the future. But wait, there's more, right? So once all the postings and work was completed, where we did things like, writing an extensive internal review, figuring out incident remediation items, and we work closely with Rafa53 to fix the bug. We spent some time writing a blog post for our engineering blog, where we explain what happened and some of the key takeaways for us from the incident. So after all of this, we started planning for the next attempt. We collected all the learnings from the incident, and we started to figure out what had to happen for us to be comfortable doing another attempt, hopefully one last attempt. So this is the last status update in the DNSSEC project channel, a few days prior to attempt number 4, where we finally enabled DNSSEC on Slack.com with no issues whatsoever. And I think this list is quite interesting, as we had various focuses. So the first one is documentation and testing. So we focused a lot on runbooks, improving our runbooks, and making sure they were really solid and they contained all the necessary steps for doing all operations related to DNSSEC. We tested SON signing key restore after the Rafa53 feature. And then we tested the key signing key restore, testing that the DNS key RRSig is the same after re-enabling or restoring this key. Then the second focus is observability. We did some work to have additional logging of DNS traffic. So we have interesting metrics like top resolvers, traffic patterns, when resolvers start asking for DS records, serve fails, and stuff like that. And we did a dashboard with all this DNS traffic and other Slack key metrics, and we keep this dashboard in a monitor, refreshing constantly during the rollout. And these additional metrics, they're nothing other than Rafa53 logs. So we basically enable the logs on the zone, and we ingest them into our logs pipeline, and we make sure that we can, keep track of all these metrics to use as part of the rollout. Then the third focus is comms. So we communicated heavily both internally at Slack and within Salesforce. We communicated with the Rafa53 team vastly, and then with the NanoG and the DNSORG groups. The NanoG is the North American Network Operators Group, and the DNSORG is a community of DNS operators, both of which contain a lot of network and DNS operators that can transmit what are they seeing in their networks and in their resolvers to us, and we can reach out to them if we need help in case of another failed attempt. And then the fourth, but not least, is the rollout plan. So we agreed on running the rollout during the lowest traffic time in the week, and we did some zone changes before enabling signing to reduce the impact time if things go wrong. And then the last one is basically stick to the runbook during the rollout, just follow the runbook precisely and stick to that. So yeah, the fourth attempt was the charm, and today Slack.com has had DNSSEC enabled for 2 months without any issues, and this is a great accomplishment for us. So before we jump into Q&A, I would like to do some acknowledgements. I would like to thank the Amazon Rafa53 team for their collaboration and for the rapid fix, the Salesforce Public DNS team for their kindness, their support, and their DNS expertise, and all of the DNS community for their invaluable help in rapidly flushing caches to bring Slack back to everyone affected by this problem. And last but not least, I want to give a huge thank you to our customer experience team, who are the ones in the front lines every day connecting the dots between our customers and their engineering teams. We couldn't have done it without you. So yeah, feel free to go ahead and read more detailed write-up about this on our engineering blog over at slack.engineering. And I am now ready to answer any questions you might have. Thank you all.
Thank you so much for sharing your experience of that outage. It sounds like it was both a long kind of time period and also a lot of very interesting learnings along the way.
Indeed. It was a good, bunch of months worth of work after the incident. So definitely a long one.
Yes, absolutely. Well, we're going to be spending some time just kind of reviewing some questions about this experience from the audience. So if anyone has any questions, please add them to the chat Rafael won't be able to join us in the Zoom Hangout later, so definitely get your questions in now, or else obviously join us on Slack for a more async question answering time. But to kick it off, I'm sort of intrigued by one of the kind of side things you mentioned during the talk. You mentioned that you spent a fairly significant time doing what I've heard described as pre-factoring, doing some work before you go into the change in order to make the architecture more friendly to the change. How did you go about kind of scoping this out and estimating this and advocating for it within the organization? Because I find people can often struggle to do that.
Yeah, it's a good question. So like most of the work is like simplifying our DNS zones. Like we work with two vendors at the moment, one of which is RAF53 and the other one is NS1. And we had like this very like convoluted like environment where we delegated many zones to NS1 because we really like some of the features that they offer for some specific like Slack features. But the thing is, we had like many other domains which were like just delegated to NS1 and we're no longer using these features. And then we had like this very complicated setup where we had to like, keep another link in the chain of trust to like, have a successful DNSSEC setup. So what we did is we went and did like an analysis on all the zones we look after. And we outlined, how many of them need to be like migrated back to their like authoritative RAF53, and we just like build up a plan. We factored that into the RFC document, and we just got sign off from like key like stakeholders saying, yeah, this is what we should do. And it's actually like extra work, but that extra work will like save us time in the future, like both in like operating DNSSEC and possible outages coming out of like like human error having to do with not establishing that chain of trust well and things like that. So the less delegations we have in this case, it's the best for us.
It sounds like it also gave you a little bit more alignment over your zones so that your rollout could be a bit simpler. You could kind of reuse some of the same across the zones, which is good.
Yeah, so, exactly. Yeah, and we had like some interesting things happening there. So some of the migrations required us to like build up like temporary zones and like shifting traffic between zones because we had to rebuild some of them in NS1 specifically. So we couldn't just like create the zone, have the traffic shifting there because it takes a while to like populate all the records. Mm-hmm. So we had to create like empty temporary zones that were not getting any traffic, then shift traffic there, then perform the operations that we were doing on that zone specifically, and then shift traffic back. So it was a fair bit of work that we had to do prior to actually getting hands-on with DNSSEC in prod.
Interesting. Yeah, I think that's this in prod kind of theme that we're talking about today across the whole track and that you touched on is really interesting, and where that phrase that everyone's testing in production, just some people are kind of paying attention to the results or focusing on that. This rollout to Slack.com is a great example of that. You'd done all the pre-work, you'd done all the testing that you could have thought of. You weren't kind of skimping and assuming you could monitor for results, and yet it was still a surprise when you ran into things. And you mentioned that before you went through, I think it was the fourth and final successful rollout, that you added some more monitoring to it, some more logging, some just more observability and telemetry. Are these things that were kind of short-term adds, or do you still find yourself using that data and finding yourself expanding in other ways?
Yeah, so they're like more long-term kind of things. Like for some zones, we figured it's not always useful to have the logs enabled all the time, but for like critical zones to us, I think it's really important that we have like that visibility always available. So in the example of like RAF53 logs, those are really important for us, and we have built like dashboards around them. So whenever we need to do like any DNS operations or like we have any like network type kind of outage, we can like quickly pinpoint if there's like a resolver, like specific resolver that's like having their traffic dipped, or we can even see like a map of traffic divided by like the client eDNS subnet. So we know like where our customers are and like which point of presence they're reaching and all this kind of thing. So it's not only like the figuring out like the errors on the requests, it's also like additional data that helps us build like more like figuring out like when's the best time to do certain things, or what should we invest in a new POP if we want to do that, and those kind of things.
Oh, very interesting. Yeah, I think for a lot of us, I've been across the infra side and the software kind of service side as well, and I think for a lot of people, each side is a bit of a black box. It's like, how do you debug DNS? What does observability even look like when you're talking about something that is as distributed as DNS and as many dependencies? Do you feel like there's any learnings that you've either brought in from the software observability experiences, if you have any, into trying to bring observability to DNS, or vice versa, your experiences in this infrastructure and DNS side of things that you feel like could enable software service owners to get even more insights into their services?
I think it's more of the like former. Like I was able to bring more like software type of doing things into like the DNS world in this case, because typically like operating DNS is just like doing changes in a zone rather than actively monitoring the traffic and all those things. And thanks to this like way of thinking, like the software development life cycle, and all the metrics that we have on our clients, or like the Slack clients, we were able to like get really valuable data, like this Slack B thing that we were mentioning. Like that was critical to us because we actually get the telemetry from the clients into like what's going on, and the fact that it goes to a separate domain, it's perfect, because any impact to our like primary domains, like our production domains, is not affecting this Slack B domain where we get the telemetry. So we can rely on this separate like ingestion pipeline to like make decisions while you're in an incident, right? Because like some of the metrics that we were seeing during this incident in particular were like everything was stable and everything looked good, but it's because the customers that were reaching us were fine, but the ones that were not fine were not even reaching us. So we didn't have like that observability at the level of Slack's infrastructure, but we had it on this Slack B portion of the observability spec.
Yes, I think there's always those kind of realizations at the wrong time when your status page is being hosted by the same infrastructure that your app is, and all of a sudden you can't even report your status being down, and that's always a bit of a facepalm moment that seems so obvious in retrospect, but doesn't always get identified up front. So
exactly,
that's really interesting.
100%.
Yeah, thank you so much for sharing all of that, Rafael, and your additional experiences here in the Q&A. I think we are out of questions for now, but the beautiful thing is we have Slack, which if you're not already in the QCon Slack, please do join, and we have a channel there, and we can keep answering questions. So thank you again for the detailed example of what can be quite a hard to debug incident.
Sounds great. Thanks so much, Javi.
Fantastic.
Thank you all. Have a great day. Bye-bye.